Welcome to the SAR channel, where sound and audio are demystified. Modulation coding is used in storage and transmission systems to make data timing self-clocking more efficient. But accurate data recovery depends on how precise the received timing clock is. If the timing of the clock embedded in the data stream is unstable, or if the oscillator driving the AD or DA converter is inaccurate, errors, noise, or unwanted modulation effects can appear in the signal. To recover data correctly, receiver circuits must reduce timing errors that occur during storage, transmission, or signal reconstruction. Phase-locked loops, PLL, are commonly used to keep the receiver's timing in sync with the transmitted signal's clock. Maintaining timing accuracy in digital systems is difficult because of noise and interference. The longer the word length, the tighter the timing control must be. For example, 24-bit systems need much more precise timing than 16-bit ones. Above all, timing stability is critical because it demands extremely strict accuracy. Jitter is any change in the timing of a signal's zero crossings compared to a perfectly steady signal. In other words, it's instability along the time axis, measured against an ideal, stable reference. In analog signals, timing changes can sound like pitch variations. In digital signals, jitter can cause bit errors or be heard as extra noise and distortion in the final analog sound. If the digital signal is properly corrected for jitter, there may be no errors or audible problems. Jitter always exists. Its impact depends on where it happens in the signal chain. While high jitter may not stop digital data from transferring correctly between devices, some equipment handles jitter worse than others. During AD or DA conversion, even small amounts of jitter can create unwanted artifacts in the analog signal. Jitter shows up as small variations in the timing of signal transitions. Around each ideal transition, there's a small window of uncertainty called peak-to-peak jitter. It can occur in stored data during transmission or in processing circuits like AD and DA converters. Jitter can appear as random timing changes in clock edges, white phase jitter, timing variations related to clock pulse width, white FM jitter, or timing changes linked to other periodic events, correlated jitter. Jitter is defined by its spectrum, which shows how strong and how frequent the timing variations are. Random jitter spreads across many frequencies, raising the overall noise floor when converted back to analog. Periodic jitter appears at specific frequencies, creating sidebands or modulated noise around the signal. Jitter at frequencies lower than the sampling rate builds up as timing errors, depending on how strong and how slow the timing changes are. When an oscilloscope is synchronized with a stable reference clock and its time base is set to 1 unit interval, it shows a group of overlapping signal transitions called an I pattern. This pattern helps assess how good or clean the received signal is. Noise appears as fuzzy or unclear amplitude changes, while jitter shows up as variations in the timing of the transitions. Other issues like peak shift, DC offset, and different types of distortion can also be seen. The quality of signal reconstruction can be checked in the same way by looking at the I pattern after processing. Noise in the channel makes the I pattern close vertically, reducing noise margin, while jitter makes it close horizontally, reducing timing margin. The amount of signal degradation can be evaluated by measuring how much the I opening shrinks, often expressed as the I opening ratio. The impact of jitter depends on where it appears in the signal chain. Timing errors between connected devices are called interface jitter, while timing errors during signal conversion are called sampling jitter. Interface jitter happens in the transmitted data clock when information is sent from one device to another. It becomes a problem only if it causes errors in the recovered signal. Receivers often use error detection circuits to monitor data quality. Because many digital data streams are self-clocking, the receiver must recover both the data and clock in sync with the transmitted signal. A receiver using a fixed clock can't follow a signal whose timing varies, even if the average rate matches. To fix this, most receivers use a phase-locked loop that adjusts their clock to match the incoming data rate. The PLL follows slow clock changes but filters out rapid jitter. It compares the phase difference between input and output, then adjusts a voltage-controlled oscillator, VCO, to reduce that error. Once locked, the oscillator runs at the correct frequency, minimizing high-frequency jitter and stabilizing the timing. However, near the PLL's cutoff frequency, some jitter may be amplified. If the recovered data has no errors, interface jitter hasn't caused problems. But if the jitter isn't removed before digital to analog conversion, it can lead to sampling jitter, which degrades audio quality. Sampling jitter happens when the timing of the sampling clock fluctuates, introducing noise and distortion in the analog signal. To reduce this, timing must be extremely accurate. Sometimes the sampling clock is derived from the same interface signal that carries data, so a PLL may again be used to clean the timing and remove jitter. Because jitter can appear at any point in the signal chain, each stage must be carefully isolated from it to ensure clean, error-free data transmission. This is especially important when several devices are connected, as each one can add small amounts of jitter that build up over the chain. Fortunately, even a signal with heavy jitter can be retimed using jitter attenuation, which restores correct frequency and phase so that the final signal stays within acceptable limits. If you've enjoyed this video so far, please hit the subscribe button for more. Thank you. Jitter can appear early in the audio digitization process, starting with mechanical storage devices. Media like optical discs may create timing errors in the output signal because of small speed changes in their spinning drives. To reduce these errors, precise clock and servo systems are needed to control motor speed, and data buffers must be used to smooth out irregular data flow. Variations in spindle motor rotation, such as wobbling or uneven spinning, cause data rate fluctuations that can be slow or rapid. If these variations stay within acceptable limits, all recorded data can still be recovered accurately, and no errors occur. Servo control circuits read timing information from the data and create correction signals to stabilize transmission. Often, a phase-locked loop is used to manage the servo. It compares synchronization patterns in the outgoing data, recorded at a fixed rate with a reference clock, then adjusts the motor speed to reduce any difference. A second PLL can handle finer speed corrections. Even though these servo systems maintain steady rotation, small timing errors may still remain in the data. Likewise, when data travels through electrical or optical links, it can pick up additional jitter. To counter this, the data is often reclocked through a memory buffer, which helps smooth out timing variations. A larger buffer can absorb greater timing differences, but also increases overall signal delay. Buffers are typically built using RAM, where the memory address counter loops continuously, forming a virtual ring. Because the read and write operations are independent, uneven input data doesn't affect the accuracy of the output. The output clock must be separate from the input clock. The amount of stored data in the buffer controls the transfer rate. If the buffer is too full or too empty, the servo adjusts motor speed to bring it back to the middle level, preventing overflow or underflow. A buffer can also use FIFO memory, where data enters at one end and exits at the other in the same order. These timing correction systems are essential when using non-continuous storage like hard disks. The buffer fills as each disk sector is read and keeps output steady between reads. When writing, it provides a continuous data flow to the disk. If the jitter is extremely small, less than 1 bit period, a buffer may not be necessary. During data transmission, interface jitter must be kept as low as possible. No matter how much jitter comes from the transmitter or cable, the receiver must handle two main jobs: recovering the data and recovering the clock. Jitter affects both, but how serious it is depends on the situation. If the received data is only stored or processed digitally, only data recovery matters. In that case, interface jitter is only a problem if it causes bit errors. However, if the data is to be converted to analog or resampled, both data and clock recovery become critical. Too much jitter can make it difficult for the receiver to extract a stable clock, leading to conversion errors. A receiver's phase-locked loop separates the clock signal from the incoming data, uses it to recover the data, and then rebuilds a clean clock to use as a stable internal reference, a process called jitter attenuation. In some systems, the receiver extracts synchronization information from the input, stores the data in a buffer, and then replays it using the reconstructed clock so the timing matches the destination device. The buffer must be large enough to avoid overflow or underflow. This process, known as genlock, keeps devices synchronized. When the sampling rate of the incoming signal differs from the system's own clock, a sample rate converter is used to adjust the timing and reduce jitter. Some receivers use a two-step clock recovery method. The first step is clock extraction, where a primary PLL locks onto the incoming clock and tracks its jitter so the data can be decoded without errors. However, this stage doesn't remove the jitter. The recovered clock may still be unstable. The decoded data is then placed into a FIFO buffer. If the jitter is very small, less than 1 bit period, no buffer may be needed. The second step is jitter attenuation, where another low jitter PLL locks to the sample clock and retimes it with high accuracy. This clean clock is then used to read the data from the buffer. Essentially, the second PLL removes the timing variations that the first PLL followed. Poor audio quality caused by jitter at the converter often originates from the receiver, not the converter itself. Cable characteristics also influence transmission jitter. One type, called pattern-dependent jitter, depends on the actual data being sent and results from high-frequency losses in the cable. Transmission systems that use fixed sync patterns avoid this type of jitter, but it can still happen when the data changes predictably, such as with low-level, single-frequency audio signals, causing timing shifts in certain bits. Formats that use data scrambling prevent this issue by randomizing the data pattern. In large systems with multiple connected devices, managing jitter becomes harder. If devices are connected in a chain without a central clock, each one extracts its timing from the previous device, which can pass on or even worsen jitter. Some PLLs remove high-frequency jitter but let low-frequency jitter through, which can build up and cause later devices to lose synchronization. To avoid this, all devices should be locked to a single master clock in a star configuration, each receiving both data and an external clock input. This master clock synchronization ensures every device uses the same stable timing and ignores jitter from incoming data. If you've learned anything new so far, please like the video. It really helps the channel grow. Thank you. Jitter must be carefully controlled throughout the digital audio path, but it's especially critical at the analog to digital and digital to analog conversion stages. Even small timing errors in converter clocks can distort the resulting analog waveform. During AD conversion, samples must be taken at precise times. If the AD clock has jitter, samples are captured at the wrong moments, producing incorrect amplitude values. Even if these samples are later sent to a DA converter with a perfect clock, the result will still be wrong because the original samples were taken inaccurately. The error size increases with the steepness of the signal, so high-frequency audio is more affected. To avoid this, converters must use high-quality crystal oscillators, precise circuit design, and proper circuit board layout. In the frequency domain, jitter in an AD converter behaves like FM modulation. The input signal acts as the carrier, and the jitter acts as the modulator. Low-frequency periodic jitter lowers signal amplitude and adds sidebands around the input frequency, spaced by multiples of the jitter frequency. As jitter grows, sidebands become stronger, and high-frequency signals are affected more. Jitter must be kept small enough not to interfere with the least significant bit, LSB, during sampling. Since jitter reduces the converter's theoretical dynamic range, oversampling sigma-delta AD converters are just as sensitive to steady sinusoidal jitter as non-oversampling Nyquist converters, but they handle random jitter better because oversampling spreads it out and filters it. DA converters also suffer from jitter. Even when the digital samples are perfect, a jittery DA clock causes the right samples to be played at the wrong times, producing noise and distortion in the analog output. The data itself may be fine, it's just read at uneven intervals. Modern designs fix this by reclocking incoming data with a clean, stable clock before conversion, often using a PLL or similar circuit. In resistor ladder DA converters, jitter causes timing errors that appear as spikes compared to the ideal signal. The spike size depends on how big and fast the voltage steps are. Larger transitions produce larger errors. The resulting noise has a flat white spectrum that increases at high levels and frequencies. Oversampling helps reduce random jitter, but not low-frequency jitter that changes slowly over time. Sigma-delta DA converters vary in how sensitive they are to jitter, depending on their design. Single-bit converters that use continuous time filters can produce jitter-related noise even when no signal is present, as jitter pulses are independent of the signal. This phase modulation can shift high-frequency noise into the audible range. Converters using switched capacitor filters are less affected because these circuits reach their final value, regardless of the exact clock edge timing, though they must filter out all out-of-band noise to work correctly. Multi-bit converters are generally less sensitive to jitter because they use multiple quantization levels and produce less ultrasonic noise, so timing errors have less influence on the clock. Some listeners claim to hear differences between digital cables, but these differences usually occur only with poorly designed DA converters that fail to recover a clean clock from the incoming signal. Well-designed converters with stable internal clocks are immune to such effects as long as the digital data itself is unchanged. Jitter control is necessary at every stage of digital audio. While special instruments can directly measure clock jitter, traditional analog tests like THD plus N, total harmonic distortion plus noise, and spectrum analysis also reveal its effects and may be even more useful. If a system can recover data without bit errors, interface jitter doesn't degrade the information. However, AD converters must be clocked precisely, and clock recovery before DA conversion is essential. In high-quality audio systems, jitter rarely causes audible problems. At normal listening levels, its effects are usually masked by other sounds. Still, as equipment evolves with higher bit depths and faster sample rates, jitter control becomes increasingly important. Ultimately, jitter is one of several distortion sources that must be minimized through good circuit and clock design. Thank you for watching till the end. To better understand each video, make sure to watch the previous ones. Some may serve as prerequisites for the next. If you have any questions or opinions, feel free to leave a comment. Until next time, subscribe and stay curious.